Hi, it's Dr. Harris, and we're here to begin talking about Chapter 2 in our statistics text. And in this chapter, we're going to be focusing on looking at uh, numerical variables and categorical variables, and looking at ways that we can provide numerical and graphical summaries for those variables. This slideshow will focus on looking at a single numerical variable. And we'll first be looking at graphical methods, and then we'll get into looking at some numerical methods for studying these variables. So here we go, introducing you to a new data set, one that we'll visit a few times over the course of the semester. A survey of a number of students at the University of California at Davis, a textbook that we've used in the past, had faculty from this university, and so we've got some data that was collected from those faculty members. And each of these students were asked 12 questions to respond to, and we can use the data, view, and help commands to take a look at these variables. So I'm going to copy and paste into RStudio. Hopefully you've signed into RStudio so that you can look at these. You can follow along and do this. Here is our UC Davis data set. We've asked about their gender, about habits in terms of hours on the TV and computer, how much they sleep, how many drinks they consume, information about their heights and their parents' heights, and a few other things as well. So we're going to be looking at a couple of the numerical variables in this data set in this slideshow. And our first question is going to be, how many hours a week do students at this college, this university, spend on their computers according to this sample of data that was collected? And it's the variable computer in the data set that records how many hours these students self-reported spending on the computer each week. And so it's a numerical variable. It's counting the number of hours that these students spend. And so we're going to examine what's called a density plot. It's a graphical tool for examining numerical variables, similar to a histogram, which you probably have some experience with in your past, but in some ways it's a smoothed out histogram. So the way our command that we're going to use to get a density plot is fortunately intuitively called density plot. And so let's take just a little bit of time to look at the structure of this command. It's at some level not too different from XY plot, which we saw in a previous slideshow. We first provide, in this case, just a single variable, and we use the tilde in front of it. So it's going to be tilde variable name, comma, data equals the set of data that it comes from. So it's going to be tilde computer, data equals UC Davis. And then we can dress it up just a little bit. Main is going to give a title to our density plot, and XLab is going to label the horizontal axis for us. And so we give a nice little title for our plot, and we describe what the variable on the horizontal axis is measuring. So again, I will copy and paste this into RStudio, and we'll take a look at what we get. And so we can see over here in our plot window, we've got a picture of it. I've also got one on the slideshow as well. You can see the title at the top, the label on the horizontal axis, just like we asked for. And so here we have a slightly less distorted picture of the density plot. And so how do we read this? Well, we can see these circles at the bottom, and they tell us where the individual data values are. And the height of the density plot gives us, relatively speaking, how many responses occur around that range. And so we see here at the bottom, it looks like there's a lot of overlapping circles, and that's where the highest concentration of values are. And so the peak of the density plot tells us where the greatest concentration is. And we can see that things sort of tail off, can become a little less frequent over here as we move farther and farther. As the number of hours reported increases, we see that there are fewer and fewer responses, and then there's just a couple of single responses way out here. A couple of students who spend many hours a week on the computer. But we want to recognize that the density plot, the height of the density plot represents relative frequency of responses in that range right around that number. So once we've got the density plot, we'd like to be able to describe it. And so there are two things that we're going to mainly focus on in terms of describing. One is the number of peaks that we have in our data set. This density plot has a single peak, one peak right here. And so we would call that unimodal. And the other thing that we wanted to just try to describe in terms of the shape of this distribution is how close to symmetric it is. And in this case, I would say that it's not particularly symmetric at all. We've got a much longer, what we would call tail on the right side of the distribution. And so the side that the tail is longest is going to tell us in what direction it's skewed. And so with a longer tail on the right, we're going to call this a right skewed distribution. So when the center, when the peak is more to the left, and we got a longer tail on the right, we're going to say that that's right skewed. So this is a right skewed unimodal density plot. To give you an example of another density plot that has a little bit different look to it, let's look at height, the heights that were reported for students at UC Davis. And so this follows the same pattern as before, tilde height, but notice that the H in height is capitalized. If you go back and look at the data set, you'll see that that's the case. So we have to be really careful about that. We say that data is equal to UC Davis. We give a title and we label the x-axis again. So I will copy and paste this in. And we get a different look this time. I'll show it to you in the slideshow. This time I've got a much more symmetric shape to it. It's still unimodal. We get the slightest hint of a second peak here. That wouldn't be too surprising. Heights, we might expect to have two peaks. Why is that? I'll give you a few seconds to think about that while we go to the next slide, but think about why it might make sense that heights might be double peaked. So this is much more symmetric as we see. It's still unimodal, but heights might be bimodal because our data set included both men and women. And so if we had many more individuals, we might expect to see a peak around, say, around 65, 64 inches for women's heights, and then again right around 69, 70 for men's heights. So we wouldn't be too shocked if there was a bimodal distribution for heights. So let's just look at some distributions of density plots to get a sense of a better feel for what does it mean to be symmetric, what does it mean to be unimodal, bimodal, etc. So here are some examples. We would call this unimodal, just a single peak, but the tail this time is on the left, and so it's left skewed. It turns out that left skewed distributions occur somewhat less frequently on average than right skewed distributions. A lot of financial data tends to be right skewed because you've got a large number of data values on the low end with just a few higher responses for things like salaries, prices of homes, etc. An example of something that might be left skewed could be a distribution of the years of coins in a collection. You might expect to have many more coins of more recent years than you would as farther you go into the past. You would see fewer coins of that year. Here's a right skewed distribution. This would be a bimodal distribution. It's not necessary to have the peaks have the same height. And so we have a second peak over here on the right side of things, but we would say that there's a longer tail on the right side. So this would indeed be right skewed. We saw something similar to this with the height distribution earlier, single peak, symmetric. We could call this bell-shaped. We'll talk about bell-shaped and normal curves in the not too distant future. Here's an example of a bimodal symmetric distribution and even a different look at a bimodal symmetric distribution. So we want to get comfortable with generating density plots and then being able to describe them in these terms, in terms of number of modes and whether it's symmetric or skewed. So that's our density plot is going to be one of our favorite tools for deciding if distribution from a graphical standpoint, looking at graphical means for describing numerical variables. I want to turn now to looking at a numerical method, and a command that we have to look at numerical summaries of a single numerical variable is a command called favstats. So even though there's not an E here after the V to make that A long, we're going to call this favstats rather than favstats. And so let's run favstats on the computer data. And we'll see we get the same output that we do on the slideshow. So we get a set of numbers, and we'll take the next few slides to describe these numbers. So first of all, I want to focus on mean and standard deviation, mean and SD here. So for this data set, the mean response is around 14.25 hours. The standard deviation is about 11.5 hours. We want to talk about what those things mean. Hopefully you're comfortable with the mean from your past. The mean is where we calculate the sum of all the responses and divide by the number of responses. The standard deviation is something that you might be a little less familiar with, though. We're going to use the symbol S in our slideshows to represent standard deviation. Sometimes we'll abbreviate it as SD. But a good way to think about standard deviation is it's some sort of average distance that data values in our set are from the mean. And so we're going to need to, and so I'm going to show you briefly how we can calculate a standard deviation for a small data set, just to give you a feel for what's going on underneath the hood when R is doing these calculations. And so the first step, think about it as a 5-step process. The first step is to compute the mean of your data set. So because we need to calculate the distances from the mean, we need to find the mean first. And then we're going to subtract the mean from all the data values. And that's going to give us what we call deviations. Then we're going to square the deviations and add those all together. We take the sum of those squares of the deviations, we divide by one less than the number of data values in our set. And finally, we undo that squaring by taking the square root. So it's going to be the square root of the sum of the squares of the deviations divided by one less than the number of data values. I'm not going to write a formula for that down for you here, but we are going to work a small example to try to see how this is in action. And I may be asking you to do this for me as well. So here's a small example. Suppose we have the 6 numbers 3, 6, 10, 14, 18, 15, and 18. It's not hard to calculate the mean. We add the numbers up. We get 66. We divide 66 by 6, and so the mean of the data set is 11. The next thing is to find the deviations. And so we're going to subtract 11 from each of these numbers. And we're going to see that in a table on the next slide. So here are my 6 numbers. And here, to get the deviations, I've subtracted 11 from each of these numbers. And so 3 minus 11 is -8. 10 minus 11 is -1. 18 minus 11 is 7, etc. So here are the deviations. This is how far and in what direction, the sign tells us in what direction these numbers are from the mean. But we're going to square each of these deviations, and so that gets rid of the negative signs that we have. And so here I've found the squares of each of my 6 deviations. I add these numbers up. And so if I add these up, I get 164. We take 6 and subtract 1 from it. If I have 6 data points, I'm going to subtract 1 from that, get 5. And so I'm going to divide 164 by 5. We get 32.8. And so my standard deviation is going to be the square root of 32.8, which is almost 5 3/4. So our data set has a mean of 11 and a standard deviation approximately equal to 5.73. Just a couple pieces of information about standard deviations, good things that we want to know. Because we're squaring the deviations in the formula for calculating it, there's never going to be a possibility for a negative value for the standard deviation. And so this S is always going to be 0 or greater, and the only way that S can be 0 is if all of my data values are the same. So think about that. If I had a data set of 6 tens, excuse me, the mean of those numbers is going to be 10. And the deviations, all the deviations are going to be 0. So when I add all those zeros together, I get 0. I divide by 5. 0 divided by 5 is still 0. The square root of 0 is 0. So I'll always get a standard deviation of 0 if my data values are all equal. But otherwise, the standard deviation will be positive. And so we say that standard deviation is a measure of spread because the greater that S is, the more spread out my data is. And so if I've got a relatively small standard deviation, that means my data is kind of tightly packed together. But if I've got a large number for S, that means that my data might be fairly spread out. And the other thing that we would say is that typical values in a data set are typically within one standard deviation of the mean. And by typical, we'll say more about this not too distant future, but typical for right now, we can think about it means, well, about 2/3 of my data. So about 2/3 of my data points should be within one standard deviation of the mean. So let's take a look at the example that we just worked. 11 was my mean, 5.73 was my approximate standard deviation. So if I subtract the standard deviation from 11 and add the standard deviation to 11, I get approximately 5.3 and 16.7. So I would say the typical values are going to be between 5.3 and 16.7. And if you go back and look at my numbers, exactly 2/3, 4 out of 6, were between those numbers. We had 3 on the outside, on the low side, 18 above. So right now we think about typical means within one standard deviation, also means roughly within about 2/3 of my data should be meeting that standard. So here's the output for phase stats applied to the computer data again. So this time I want to focus on these first 5 numbers that we've got here: min, Q1, median, Q3, and max. Q1 is called the first quartile. And what that means is that it's about the 25% mark of my data. About 25% of my data values should be below this number. The median is the midpoint of the data. It splits the data in half. So half of the data should be below the median, half of the data should be above the median. And the third quartile focus is going to be the 75% mark of the data. And we would say that about 75% of all the values are below the third quartile. So quartile, the prefix quar, makes us think of 4. We're dividing the data into 4 equal parts, more or less. First quartile marks off the first fourth. The median is sometimes also called the second quartile. And then the third quartile would mark off the third fourth. The interquartile range, IQR, stands for interquartile range. That's the difference between the third quartile and the first quartile. In this particular case, that'd be 20 minus 6 or 14. And so this tells me that the middle 50%, the numbers that are between the first quartile and the third quartile, comprise the middle 50% of my data. And this tells me how far apart the first quartile and third quartile are from each other. And so in some sense, that's a measure of how spread out my middle half of data is. And so when you hear the word average, we tend to think of the word mean, but average mean is a little bit more generic than that. The mean is a kind of average. The median is also a kind of average. And so the middle value of a data set is another measure of the center of the data. And as I mentioned just a couple minutes ago, the interquartile range is in some sense a measure of how spread out the data is. Min, I didn't comment on this at the time, but min references the absolute minimum value that was the minimum response we had for this data set, and the max is the largest value. And so somebody said they spend no time on the computer each week, and then at least one person said they spend 84 hours a week on the computer, which is more than I guess it's about a half a week. It's 12 hours a day. And so the 5 numbers together, minimum, Q1, median, Q3, and maximum, together form what we would call the 5-number summary for a data set. So let's take a look at how we can how we can graphically represent the 5-number summary. And we get something called a box plot. And the command for us in RStudio is bwplot. And I'll tell you in a minute what the W stands for. But the command is not boxplot, it's bwplot. And if we don't worry about labeling anything, we can just give the variable name, again, tilde variable name, comma, data equals the data set it comes from. And so here's bwplot, and we'll get what we call box and whisker plot. The W stands for whisker. And so we can see the box and whisker plot here. I've got it in the slideshow as well. And so I want to talk briefly about how we interpret this box plot. So we want to remember that first of all, the median response was 10. If we go back and look at my 5-number summary, the median response was 10. And we see that in the box and whisker plot represented by this dot here. So if I just drop down to my axis, straight down, it looks like this dot is centered over 10. And so this dot represents the location of the median of the data set. So we want to keep that in mind right here. This dot, median. Then around the circle, the dot here, we've got a box. And so this is the box part of the box and whisker plot. And when we've got our variable represented horizontally, it's the ends, the left and right ends, that tell us about the quartile location. So here, this left end of the box is hovering above the first quartile. Our first quartile in this case was 6. So 6 is right here on my axis. The right edge of the box is going to be the third quartile. Our third quartile was 20. And so this number right here is centered right over 20. And so we draw the circle, the dot, over the number that represents the median. And then the left and right edges of my box are going to be over the first quartile and the third quartile. So that takes care of the median and the box part. And then we've got these things that we might call whiskers attached to the box. And at first, it might make sense that you think, well, the whiskers are going to extend out to the minimum and maximum. And sometimes they do, but not always. And in this case, the left whisker does extend to the minimum response, which is 0, but the right whisker does not extend out. It only looks like it goes out as far as 40. And then these two numbers here, 50 and 84, that are represented as open circles, and those are representing outliers for us in our data set. If you go back and think about the density plot, we saw those two numbers that were pretty far way above all the other responses. And so now let's talk about how do statistical software determine what constitutes an outlier. So the whisker does not extend to the minimum and maximum. It extends to the lowest value and the highest value in our data set that are not flagged as outliers. And so how do we determine what makes an outlier? The definition that's being used here, and it's pretty commonly used, is that an outlier is going to be anything that's more than 1.5 standard deviations below the first quartile, or more than 1.5 standard deviations above the third quartile. So we're going to do a computation here in just a minute to see how we see that 50 and 84 get flagged as outliers here. So we need to know the value of the standard deviation. We're going to multiply the standard deviation by 1.5, and then we're going to subtract 1.5 standard deviations from the first quartile and add it to the third quartile. And that's going to tell us what range of values constitute, quote, normal values and non-outliers. So here we go. The standard deviation was about 11.5 if you go back and look at fave stats for this data set. So if we take 11.5, multiply by 1.5, we get 17.25. And so I'm going to subtract 17.25 from the first quartile. The first quartile was 6. 6 minus 17.25 is negative 11.25. And 20 plus 17.25 is 37.25. So anything below negative 11.25 and above 37.25 would be considered an outlier in this case. Now, since we're talking about number of hours spent weekly on a computer, it makes no sense whatsoever for us to have negative responses, and so there are not going to be any low outliers. But we do have two responses that were above 37 and a quarter. That was the 50 and the 84. And so that tells us that those are the ones that get flagged as outliers. So which should we use? Should we use mean and standard deviation, or should we use um, five-number summary for our to report back as a numerical measure for a numerical variable? And the answer is that it depends. If the data is skewed or has a lot of outliers, we tend to think that the five-number summary is going to be better. But if our data set is relatively symmetric, then we're going to use the mean and standard deviation. So the bottom line is we want to uh, look at the data first. That's always our mantra here is going to be look at the data, do a density plot, and so then you can tell how symmetric or skewed it is. If it's symmetric, mean standard deviation. If it's skewed, we'll want to use the five-number summary. Why is that? The median is a more stable representative of the center when we have skew or outliers. And so that's why we're going to want to try to use the five-number summary in that case. We'll be back soon with more on summaries for categorical variables.